Okay, so today now we speak about a generalization of the Gaussian channel we have seen so far. In particular, we consider parallel Gaussian channels. And we use now the complex circular symmetric model because these parallel Gaussian channels are in fact very much motivated from communication theory, and therefore it makes sense to focus on this model specifically and use complex numbers as we have explained. So the model is now that the input of the channel is a whole vector of symbols of dimension k. And instead of having just a single gain that attenuates the component of x, we have now a diagonal matrix. So in other words, imagine the following. We have simply our Gaussian channels, but now we have many of them in parallel. We send at time I the component x I, actually 1i, x 2i, x ki. So these forms the input vector of the channel. Each of these components is attenuated by a different coefficient. So here there will be coefficients g1, g2, gk. The noise z1i, z2i, zki, and we receive y1i, y2i, yki. So the output is also a vector. So overall, this can be written as x at time I vector, y at time I vector equal to the diagonal matrix G times x at times I vector plus z times I vector. So this is the K parallel channel generalization of what we have seen before. And what makes this problem interesting is that now there exists a total energy per symbol constraint that goes across the channels. So in other words, we have a total energy budget to spend in one symbol, which is this ES, indicated as before. But we can allocate this energy in a different way across the channels, satisfying this total budget. Because of course, if we have an individual budget, ES1, ES2, ESK for each individual channels, then the capacity will be trivial. It's just the sum of the capacities. In general, when we have a parallel of channels and there is nothing that connects them, no common constraint, then capacity is the sum of the capacities. But in this case, there is the input constraint, as you can see from here, connects these channels. If we put more energy in channel 1, then we have less energy to spend in channel 2 to K. So this is called power allocation across parallel channels, and the capacity will be the solution of this optimal power allocation. So in general, let's fix the optimization in two steps. Step number one, we want to maximize the mutual information. Now the mutual information is between a vector, k-dimensional vector x, and the k-dimensional vector y. And the maximization is over all distributions over k dimensions, so all k dimensional distributions of the input that satisfy the input constraint. Remember that this symbol applied to a vector means sum from 1 to k of the components. Magnitude square is the square 2 norm, which is exactly what is written here. So, acting as before, we use the additivity of the noise to write the mutual information in terms of the difference of these two entropy. This entropy depends only on the noise and therefore is independent of the optimization. And then we can simply do the following. We already know that in order to maximize this differential entropy, we have to let all the component of X Gaussian and independent of each other, so the independence bound to the joint entropy holds with the equality. And then we simply say, okay, we have these Gaussian components, so without loss of generality, now a Gaussian distribution is defined by its mean and its variance. The mean can be taken as 0 because, of course, is irrelevant. Changing the mean will not change the differential entropy because differential entropy is, of course, invariant to translation, and changing the mean means simply adding a constant. So we can take the mean as 0, and therefore we can fix the variances to be, so the variance of subchannel K is ES sub K. And then the optimization reduces to the maximization over the energy per symbols in the individual subchannels, subject to the sum constraint of this expression, which is, again, the sum over the subchannels of the capacity of each subchannel for assigned energy per symbol. So if we have individual constraints, we are done because the ESK are fixed, and then this is the capacity. If we have a sum constraint, like in this case, then the problem becomes more interesting because we have to solve this maximization. Okay? So this maximization is a typical example of convex optimization. Why is that? Because the constraints is convex, so these ESK are non-negative, and the sum must be less or equal than some total ES. This is a convex set. For example, if it was in 2 dimensions, we have this simplex because this will be ES here, this will be ES here, and all the non-negative 2-component vectors ES1, ES2 satisfying that the sum is less than ES and the components are non-negative belong to this triangle. Okay, that's a convex set, and then you can generalize it in k dimension. And the objective function is concave because well, log is concave in its argument. The sum of logs is a concave function of the vector of energies. So we want to solve this problem. And how do we do this? Well, we use the same method that we have seen already mentioned while we discussed the maximization of the mutual information with respect to a probability mass function. So we write down the partial Lagrange function for this problem by taking the objective function and subtracting lambda, which is the Lagrangian multiplier, times this constraint. And then we deal with the non-negativity constraints by discussing what happened at the boundaries of the domain. And so the Lagrangian function is this. This is the objective function, as you can see. And then we have minus, and this is the constraint. So intuitively what happens, we want eventually to maximize with respect to the ES, to the okay, I have written ESK and now this is the EKS, so this is a typo that I have to correct. So we want to maximize with respect to the energies, but in order to impose the constraint, we will also minimize with respect to lambda with the condition lambda greater or equal than 0. So lambda is greater or equal than 0, because when the constraint is violated, so when this sum is bigger than the constraint, then the minimization with respect to lambda simply let lambda go into infinity. This part becomes minus infinity because this difference is positive. Minus lambda times this difference goes to minus infinity, and therefore, of course, this cannot be the solution. So in other words, again, the concept is every time you find a point that violates the constraint, the minimization with respect to the corresponding Lagrangian multiplier punishes you and imposes that this cannot be the solution. Okay. So the method consists of studying the stationary point of this partial Lagrange function with respect to the primal variable. The primal variables are the original variables of the optimization problem. The new variables that we introduce, like the Lagrangian multiplier, are called the dual variables. Lagrangian multipliers and dual variables are synonyms in this context. So differentiating with respect to a specific ESK, we find this derivative, and this derivative has to be non-positive in the following sense. As usual, if I take the cross-section of this function, if the solution of letting this derivative to 0 is strictly positive, well, then it's okay. We are here. That's a maximum. If the solution is negative, then we have to see what happened at the boundary. It means that the solution will be 0 and the maximum is obtained at the boundary when the derivative is non-negative, and therefore you can only decrease as you increase the corresponding component. So we study the solution of this inequality. In fact, first with equality, hoping to find, as we did for the Blech-Hartree-Moto algorithm, if you remember. In this case, we had nothing to discuss. What happened here? Okay, nothing to discuss because automatically the solutions were all non-negative. It was exponentials. So in this case, the discussion of what happened at the boundary was irrelevant, but in this case it is relevant. So we set this inequality with equality and we find this candidate solution. Okay, now this candidate solution of course depends on the value of lambda. This may or may not be positive. It is positive if 1 over lambda is in fact bigger than, let's say, greater or equal than n0 divided by gk square, and it is negative otherwise. Okay, so, and then you say, well, but how do we know the value of lambda? Well, we write down the solution for a generic lambda, then we replace the solution into the constraint, and then we find the lambda that satisfies the constraint with equality. So the solution is like that. For a given value of lambda, so in other words, since lambda appears always as 1 over lambda, I can call it nu, okay? And say 1 over lambda, I call it nu. You can re-parameterize the Lagrangian multiplier as much as you want because they're just auxiliary variables. Then it turns out that when this difference is positive, then we have found the stationary point with respect to the variable, the k primal variable. When this difference is negative, then it turns out that replacing ESK equal to 0 yields a non-negative derivative, because what happens if, let me write it in this way. I need space because so if nu is greater or equal than n0 over gk square, then the solution is ESK k star equal to nu minus n0 divided by gk squared, and this in fact is greater or equal than 0. And so we are happy. If nu is less than n0 gk squared, I am tempted to say in this case the solution should be ESK equal to 0. ESK star is 0. But I have to check the sign of the partial derivative. So let's replace ESK equal to 0 in the partial derivative, so in here. What happens? If I replace ESK equal to 0 in here, this denominator becomes 1 because ESK is 0. So I find that the partial derivative is gk squared divided by n0 minus lambda. Lambda is 1 over nu. And what is the sign of this? Well, the sign of this, if this is the case, then the sign of this is necessarily negative, because it means that you see from here, if I invert each side, and of course this changes the verse of the inequality, I have the 1 over nu is bigger than gk squared over n0, so this term is bigger than this term, and therefore this difference is negative. Okay, so this confirms that in the condition nu less than n0 divided by gk squared, then the solution is ESK star equal to 0. So we have the boundary point. So putting these two things together, we can write ESK star as the positive part of the difference nu minus n0 divided by gk squared. Positive part means this is equal to the argument if greater or equal than 0, or 0 if the argument is negative. And the positive part is like the truncation at 0 of what's inside. So that's our solution. Our solution is, after discussing the boundary, ESK star is simply the positive part of the difference nu minus n0 divided by gk squared. And now we have to find the value of nu. How do we find the value of nu? We replace this back into the constraint equation. So in order to find the value of nu, we have to solve the equation sum from 1 to big K of ESK star, which is nu minus n0 divided by gk squared, positive part, equal to the total ES. Okay? In principles, we have to solve this equation, which is a non-linear equation because of this positive part, so it requires some care, but we have a single parameter. We can solve this equation, find nu, and the solution will be unique because the problem is strictly convex, and so has a unique maximum. And so in this way we solve for the value nu star that basically obtain the constraint with equality, right? Then we replace back the nu star found, and what is our objective function? Well, our objective function will be, so our capacity, say C of ES, capacity cost function, will be sum over K of logarithm of 1 plus, now we have to put here ES K star times gk squared divided by n0 So we can write this as, we replace the expression of the ES. So we have, let's write it this way. And here we put nu star minus n0 divided by gk squared with a plus. And now we notice that when this difference is positive, then what we have that this term times this term gives me -1, that's simplified with this +1, and so we have simply nu star times gk squared divided by n0. When this difference is negative, then the positive part is 0, and therefore we have log of 1, and log of 1 is 0. So we can compactly write this in the following form. Positive part of log of nu star times gk divided by n0, because you can check that when the difference is negative, this product is less than 1. Log of something less than 1 is negative, take the positive part, we get 0. When the difference is positive, then we have exactly this expression. And this nu star gk squared divided by 0 is greater than 1. Log of something greater than 1 is positive, and therefore the positive part doesn't change it. Okay, so that's a compact way of expressing the solution. So the key step at the end is finding nu by solving this equation. And today in the discussion on Zoom, we will see how to do it systematically. Okay. In fact, you do it through a computer if you have a large problem, but it is possible to find the solution of this equation explicitly by pen and paper. Is very easy when you have when k is not very large, so you can do it with pen and paper. It's totally easy, but the only thing is to be careful in discussing this positive part, because in fact we do not have only one linear equation, we have a set of linear equations. We have to find which one is relevant. Okay. So we will discuss this later because there are some exercises that I have posted that requires the explicit solution of this equation. So this type of power allocation, we call power allocation because allocating energy per symbol, since symbols are transmitted at a certain rate. So eventually we have seen that energy per symbol is related to power once you establish the bandwidth of the signal. So allocating the energy per symbol across the subchannels is called power allocation. And this specific power allocation is called water filling. What is called water filling? We will see later why, but basically let me give you here a picture, and then we will go more over. So basically, look at what we do here. Look at this equation. Here, this equation. Okay. We are comparing the levels n0 divided by g squared with a single level nu. And basically the energy is going to be this difference when this is positive and 0 when the difference is negative. So in principles, the picture can be as follows. Imagine that we have our parallel channels here, and we plot these levels n0 divided by g squared for each parallel channel. So without loss of generality, let's assume that channel 1 has the largest gain, so this will be channel 1, and therefore it's so the other way around. And channel 1 has the smallest gain, so the value n0 divided by g squared is large, And then we have channel 2 has the second smallest gain, so it's this value n0 divided by g squared is the second largest. And then we have channel 3, and then we have channel 4, and etc., and channel 5. Let's say we have 4 to 5 parallel channels. And so these creates a sort of landscape of these values that can be seen as the bottom of the sea, and then we pour water. We pour water at a level, a common level nu. For example, let's say at this level, such that the sum of the differences, when those differences are positive, is given by the total energy. So what is the sum of the differences? Will be the sum of this level time plus this level plus this level, right? And we want that the sum of these three makes total ES. And oh, this is no, okay. And there are some channels for which, it may happen that the sum is negative. Sorry, the difference is negative, which means that the red value is higher than this blue level nu. And those receive zero energy. So for all the, let's say, emerged land here, out of the sea, the level of the sea, we have a zero energy allocation. It means in this case that channel 1 and 2 are too bad to deserve any energy allocation. And those levels here, those blue levels, are ES3, ES4, and ES5. So this is the graphical interpretation of the equation we want to solve. Is find level nu such that the sum of the level of the water in each subchannels, represented by this graph, is equal to ES. Of course, if we have a bigger ES, suppose that this is the solution for ES equal to 10, and now I have ES equal to 100. Well, in this case, I can afford a much bigger nu. And then it may be that also the other channels, the bad channels, receive some positive energy. Eventually, for very, very, very large total energy budget, all the channels will receive some energy unless their gain is zero. If their gain is zero, these red squares, red rectangles here go to infinity, and therefore they will never receive any energy, which means if you have a useless channel, because basically if the gain is zero, the signal is not received on the other side, there is no point in putting any transmission power on a useless channel. Okay, that's kind of engineering-wise obvious, but of course mathematically we see here. So this power allocation across subchannels is called water filling because of the interpretation of this picture. And in fact, it's called Shannon's water filling because this was one result found by Shannon. And in the modern days, because energy, or say signal power, corresponds to bits, because remember, now we have a certain signal power in each subchannel corresponds directly to the bits per symbol that we transmit over that subchannel, right? And of course, this may be zero for subchannel that receive no signal power. So, in other words, in the Gaussian channel world, transmit energy is directly connected to bit per symbol, and therefore these algorithms that allocates energy across subchannels are called also bit loading or bit allocation algorithms. And bit loading is precisely what is done, for example, in standards like DSL, in DSL, we have basically, in a way that we are going to see in a second, we can decompose the transfer function that represent the transmission cable from transmitter to receiver into a set of parallel channels in the frequency domain, and then we can do the bit loading over these subchannels, and this allows to achieve very, very high rates, hundreds of megabit per second on the same copper wire that were used to transmit voice to the home from the local box in the underground to your home or to your apartment in the old-fashioned telephone line. So this is why, without putting fiber to the home, now it's possible to receive internet at home through the DSL line at hundreds of megabit per second, and therefore stream whatever you want, Netflix, etc., to the same copper wire that were used before to deliver voice. And you don't remember because probably you were not born yet, but there was a intermediate phase where people started using telephone lines for digital transmission, and it was believed that these telephone lines should have, they were designed to transmit voice, and therefore people tried to squeeze digitally modulated signals in the same bandwidth of 8 kilohertz that were designed to transmit the human voice. And in 8 kilohertz, you can barely transmit. From the formula before, from the formula we have seen, when the bandwidth is 8 kilohertz, well, this number can be large. Maybe it can be, I don't know, 2, 3, 4, if you're lucky. Depends on the signal to noise ratio. And so you may get, like, say, for example, 4 times 8 is 32 kilobit per second, maybe 64 kilobit per second. And these were the famous line modems that you see in certain old-fashioned movies in the 80s, like, for example, War Games. If you ever seen this, well, there is this kid that uses his telephone to connect his PC at home to the server of a military bases, and then it will, plays with this computer in the military bases. The computer thinks that it's a Russian attack and launches or threaten to launch nuclear missiles. These were at the time of the Cold War. And now, of course, this was, in a certain sense, not a limitation of the piece of copper that connects your home to the station in the ground. Is a limitation of the fact that there was a filter that imposed that because this was designed to carry the human voice, this was filtering a channel that was good for the human voice that has a limited bandwidth. So what people have done is that instead of just forgetting and putting fiber to the homes, in some places they did, but it cost a lot of money, then technology said, okay, why don't we just change the boxes? Why don't we just, on the home side, you have a Fritz box or whatever, a wireless router with a DSL port. And on the ground side, so on the operator side, instead of this a box that was designed to receive the human voice, people put a DSL modem, and it turns out that the bandwidth of the copper wire is much larger, but it is frequency selective. So it has a transfer function that looks like, if I do this, it looks like, if I plot this over the frequency, the transfer function over a certain bandwidth much larger than 8 kilohertz, maybe a few hundred megahertz, but it looks very frequency selective. so has a transfer function for which if I slice this into many small parallel channels over frequency, they have very different gains. Some of them have very good gain, some of them have very bad gain. And then what you do? Well, you need to do bit loading, which is allocating the total power budget over these channels, and this is done more or less with some limitation due to practicality, more or less by the Shannon water filling solution. Okay, so now after this sort of preamble, we are going to look specifically how this is done for a class of channels that is very close now to a physical model. The class of channels is the so-called Gaussian channel with intersymbol interference, where basically the channel is represented in discrete time as a discrete time linear system, so a discrete time linear system with a certain impulse response, and therefore the input-output relation of the channel is this. There is a convolution of the input x with the impulse response g, so we have an impulse response g0, g1 until gl. You recognize this is discrete time convolution of the input with the impulse response. So this is the response, see, the output of a linear system with this impulse response and the input, the sequence x. But at the output, apart from this linear filtering, there is additive noise. So this channel is called Gaussian channel with ISI. ISI means intersymbol interference because, as you can see from this equation, when we receive sample I, yi, this is the contribution not only of x sub I, but is x sub I minus 1, x sub I minus 2, until x sub I minus L. So we have a whole window of symbols. Imagine that we have here the sequence of symbols sent. This is x sub I, this is x sub I minus 1, this will be x sub I minus 2, this will be x I minus 3, etc. until x I minus L, and then there are symbols here and symbols here. In order to form y at time I, well, we have the sum of all these symbols weighted by the impulse response coefficients plus noise zi. And then everything moves one step forward, and we keep doing this sort of sliding window filtration of, you may recognize this as what is called a FIR filter, FIR, finite impulse response discrete time filter applied to the sequence x, and this models exactly a linear time invariant system with a finite length impulse response. Why finite length? Because all communication channels are, stable. They are not systems that go into oscillation. If they go into oscillations, then then something is wrong with your design. Communication channels dissipate energy, so they are stable. So whatever impulse response you have, you can always, well, this will vanish when you wait long enough, and therefore you can truncate, and then you can, without loss of generality, think about a finite impulse response filter. Okay? So how do we tackle this problem? This channel does not belong to the class of memoryless channels because, you can see it from here, the output symbol at time I does not depend only on the input symbol at time I, but on a whole window of present and past symbols. So the channel has memory because it means that at a certain time the output depends not only on the present symbol but also on the past symbols. So this is a model that channeled with memory, and therefore we are in trouble because we do not have developed a general theory of a capacity for channel with memory. So in order to tackle this specific problem, we are going to use a trick. And this trick is in fact what is also done in practice by something called OFDM modulation. And in fact, what we are going to do is like the information theoretic version of OFDM. So how do we reduce a channel with memory to a channel without memory? We use the idea of making big blocks. Making big blocks means the following. We can do the following. Imagine that we have this sliding. So I want to now make the following picture. Imagine that this is the time axis, and this is the sequence of transmitted axes. Okay, and now you have to imagine this sliding window. So we have this impulse response that is of finite length, in fact, L plus 1, because from 0 to L, which is sliding in this direction. And every time, every step is going to take the product of the corresponding coefficients with the corresponding window of symbols, sum them together, add noise, and then you get yi, and then you move one step in, and then you get yi plus 1, etc., etc. Okay? So, if I consider a big block of symbols, for example, starting from here, I consider a block of n symbols, okay? Where typically n is taken much larger than L, so the length of this block is much larger than the length of the impulse response. And then I use the following trick. Instead of sending just the sequence X, I consider these blocks and I form the transmitted sequence by taking the last L symbols here and copying them in front. This is called cyclic prefixing. So for every block of n symbols, I create a cyclic prefix by basically copying the L final symbols to the beginning. Then you can see that the symbols taken from this point to this point, so we have n output symbols, can be seen as the so-called cyclic convolution of the impulse response with the block of n symbols. It's cyclic convolution because you see we have this cyclic prefixing, so it is as if this block was written in a circle and the sliding window was moving like this, was moving from here until back here, okay? So this becomes a cyclic convolution, okay? And now what we can do is that we can stack all these blocks, each one with this cyclic prefix, one after the other. So instead of sending simply X, we are going to send the following thing. We have a block of fresh symbols, of n fresh symbols, and its cyclic prefix. This is just this part copied here. Then we have another block of fresh symbols here, and its cyclic prefix. Okay? And we keep going like this. Cyclic prefix, block of n symbol. And then, as we send this sequence through the channel, we only sample from here to here. Then you see these symbols from the last symbol here to the first symbol here contains garbage because the impulse response will overlap with the previous block and then and the next one. So this is called interblock interference. Interblock interference, and we just discard this because this mixes the blocks. Then we take, again, these samples here, and then we have a small interval of L interblock interference that we discard, etc., etc. So at the end, we take only these blocks of, let's say, good inputs that, good outputs that depends only on inputs from the same block. And then we can write this channel in a block form as follows. We can write a whole block of output symbol at, let's say, block time I equal to a matrix G that depends on the impulse response times the block of input symbols at time I without the cyclic prefix because we have discarded it, plus a block of Z. And now, magic, we recognize that with this trick, we have turned our channel with memory, with inter-symbol interference, into a block channel without interblock interference because we have discarded the interblock interference. And this is almost similar to what we have just studied. Look at what we have just studied. The parallel Gaussian channel model has the same equation. What's the difference here? The difference is that here the matrix G is diagonal. So we have exactly this parallel channel model. But here the matrix G is not diagonal. In fact, it expresses a cyclic convolution. The matrix G is circulant. Circulant means that the first element contains, look at this picture. The first element contains the contribution of the first symbol here and the last L symbol here. So it's done by G0 here, all zeros, and then GL to G1 here. The next corresponds to a cyclic shift of this row to the right. So we have G1, G0 here, and then here is GL. So at the end, if you keep going like this, there will be a triangle that contains the cyclic shift of the impulse response and a band that contains a cyclic shift of the impulse response where G0 goes from the upper left corner to the bottom right corner, and a little triangle here that contains the tail of the impulse response that is turning around. So matrices of this kind, that for which every row is a cyclic shift of the first row and every column is also a cyclic shift of the first column, are called circulant matrices. Okay, so this is the story, and we do this sort of cyclic prefix pre-coding that consists of adding the cyclic prefix to each signal block, and at the end we end up with the following representation. I don't know why this has become small z, so this should be a big Z. Okay, there are a lot of typos in this slide. What is this? A lot of typos in this slide set that I will correct. And this symbol here means basically take, the first column here consists of the impulse response written from G0 to GL here, and then with trailing zeros, and then do the downshift of every column and construct the circular matrix. Okay. So we are almost there. That's almost the model we have studied before, but now the problem is that this matrix is not diagonal, it's circulant. So what we have to do is another step, which is the diagonalization of this matrix by precoding. And it turns out that we are going to use this fundamental property of circulant matrices, that any circulant matrix, any k by k circular matrix is unitarily similar to a diagonal matrix. Unitarily similar means that we can write G as unitary matrix transpose times diagonal matrix times unitary matrix. And this unitary matrix that makes this diagonalization, if you want, the matrix of eigenvectors of G, for every circular matrix is just the so-called Fourier DFT unitary matrix that contains the element KL are given in this form. You can check that matrix is constructed in this way. You have the property that F Hermitian F equal to F Hermitian F equal to identity. Those are matrices that are called unitary, okay? And these precisely defines an FFT. Multiplying by F is equivalent to computing an FFT or a DFT. Well, you use the FFT algorithm to do it fast, okay? So, in other words, it turns out that the elements of the diagonal here, so the eigenvalues, if you want, of this circular matrix G are precisely the DFT of the impulse response, because when you write this product explicitly, what is this? Well, this is that the GK is equal to, this is square root of K and square root of K simplify, so you do just the kth row of this matrix times the column. This will be sum from L0 to L G L e to the minus j 2 pi divided by n KL. And this is exactly the equation of the DFT, discrete Fourier transform. Okay? So, in other words, discrete Fourier transform implemented efficiently as the FFT algorithm is able to diagonalize the circular matrix. So at this point, well, this is exactly what I wrote. The proof of this, you can do it as a homework. You have to carefully write down this product and you will see it works. But okay, maybe if time, we do it explicitly in the live session. So now the idea is simple. We take the following thing. We consider a block of symbols that I will call xi check, with this little check here, to distinguish from xi. Before sending them, we apply inverse Fourier transform by multiplying by F Hermitian. So from xi check, we obtain the block xi. Then we do cyclic prefix to these blocks and we send it through the channel. We collect the corresponding block of yi's and then we apply DFT by multiplying by F, obtaining the output yi check. Okay? It turns out that if the original channel was yi vector equal to matrix G circulant times xi vector plus z vector. Now I consider yi check, which is f times yi, which is f times g, and I replace to x f Hermitian xi check plus, and now I have f z. It turns out general property of Gaussian IID vectors is that you can multiply them by a unitary matrix and they will not change their distribution. So I call this z check that has exactly the same statistics as z. as you can see here. You can see it here. The statistics of Z check is exactly the same as Z. It's zero mean with IID components with variance and 0 per component. And here what we have, that now these, since we know that our matrix G is F Hermitian diagonal times F, now we have this matrix is F times F Hermitian diagonal F times F Hermitian. This is identity, so this matrix is exactly the diagonal. So this Fourier, discrete Fourier transform pre-coding and transformation at the output diagonalizes the channel. It can be interpreted as going from the frequency domain to the time domain. So the check symbols are in the frequency domain. We use an inverse Fourier transformation to go from frequency to time. The symbol without the check are in the time domain. We generate time domain samples. We introduce the cyclic prefix and throw away the interblock interference at the receiver in order to turn the linear convolution into a cyclic convolution. And then we go back to the frequency domain by applying the transformation F, which means discrete Fourier transform of the output. We go back to the frequency domain. It turns out that in the frequency domain, the channel decomposes into a set of parallel channels. And this is precisely the picture that I showed you before when I was talking about DSL. I said, well, we have a channel with some transfer function, and we slice this channel into tiny parallel channels in the frequency domain. Each one has a very small bandwidth, so in each of these bandwidths, the channels look like constant, so frequency flat, there is no intersymbol interference, but they have different powers, okay? So then we have to allocate the energy across the frequencies. So this is exactly what the scheme called OFDM, orthogonal frequency division modulation, that has exactly this, uses this idea of Fourier pre-coding and transformation at the output to go from frequency domain to time domain, and uses precisely the cyclic prefix in order to turn linear convolutions into cyclic convolutions. So this is called CP, cyclic prefix OFDM. There are several other versions of OFDM, but this in fact is used virtually everywhere. It's used in Wi-Fi, is used in LTE, is used in 5G new radio, uses in a lot of standards. And in the context of DSL, for cable transmission, for some reason, this is called discrete multitone. But discrete multitone and cyclic prefix OFDM are in fact the same thing, simply developed by two different groups of people working more or less in parallel. Okay. So, long story short, here is what happens, more in a pictorial fashion. An OFDM transmitter consists of mapping frequency domain symbols into time domain symbols by an inverse discrete Fourier transform, adding the cyclic prefix, and then parallel to serial conversion, and then send these symbols one after the other through the channel. And the OFDM receiver, where we have a sampler here, right, that produces the YIs, we convert serial to parallel, we remove the interblock interference or cyclic prefix portion, and then we apply DFT to go from time domain to frequency domain. And this whole operation reduces the channel to a set of parallel channels in the frequency domain for which we know exactly what to do. We know, for example, the capacity formula is going to be exactly what we have. Now we are interested in capacity per symbol, but we are transmitting sequentially a block of capital K symbols plus the cyclic prefix of L. So we have a factor here, which is number of symbols we transmit at the denominator K plus L, and then we multiply and divide by K. So here we isolate this expression, which is the capacity per dimension, per symbol. You recognize here the same formula of the parallel Gaussian channels we have seen before. And then we have this penalty factor. This penalty factor is the redundancy to introduce the cyclic prefix. And of course, this penalty factor becomes arbitrarily close to 1 for K much, much larger than L, which means our blocks must be much larger than the length of the impulse response, which means, in other words, that if you have here your spectrum and your channel transfer function, you need a lot of subcarriers, so you need a small intercarrier spacing in order to have K subcarriers in the same bandwidth. Okay, so the more subcarriers you have, the more efficient you are in principles. In fact, for example, for DSL, where the channel is very frequency selective, so it's very wiggly and is completely time invariant, so we can use a lot of subcarriers. People use 8,000 subcarriers, like very large FFTs, to have this high efficiency. In wireless, we use much less subcarriers because there are other effects. The channels, in fact, are time varying because people move around, and if the channels are time varying, then big time variations over the transmission will create other problems that are not taken into account by this theory, because here we have assumed that the impulse response is time invariant and the channel is a linear time invariant system. For time varying channels, the problem is even more complicated, and then you have to be more careful. But this goes beyond, at the moment, goes beyond what we can treat rigorously here. Okay? So at the end, what we can do, if the channel is really time invariant, we have no limit in making K big, so we can make a really, really large FFTs with a lot of points. So in the limit for K going to infinity, what happened? This coefficient K over K plus L is finite, so this goes to 1, and this sum dividing by K and summing becomes an integral over the frequency domain. In other words, it's like saying the DFT becomes like a Fourier transform. You go from discrete frequency to continuous. And it turns out that with some not too big effort in the theory, you can prove the following rigorous result, that as we let the energy per symbol is simply we have P. P is the input power in terms of energy per frequency domain symbol, and we used ES to consider to denote the energy for a block of K symbols. So the equivalence here is that the ES is equal to KP, and by making this substitution, we can look at the limit. We can express the capacity in terms of bit per symbol as a function of this transmit power. By letting K go to infinity, this sum becomes an integral, so we end up with this expression. And the equation that determines the water level also becomes an integral, because, the equation originally was some from 1 to k of nu divided minus n0, and then this is gk square positive part equal to es, but now es is k times power p, this is big K. We divide everything here, so we get 1 over k here, and this becomes equal to p, right? And now this 1 over k sum becomes also an integral when k goes to infinity, and so we have this equation. And where now instead of gk we have g of psi, and psi is the digital frequency. Remember that in discrete time signal processing, the frequency axis goes from minus 1/2 to 1/2, and then it repeats itself periodically. And when you go to continuous time, then basically the frequency goes from minus infinity to plus infinity. In discrete time, everything is periodic, and we look just at the fundamental period from minus 1/2 to 1/2. That's why I don't call it F, I call it psi. Psi denotes this frequency domain for discrete time signals, and F denotes frequency domain for continuous time signals. So the picture then is the following. In general, we have a channel which is located around a certain subcarrier, has a total bandwidth W, and has a finite transfer function. So what we do to do the beta location, well, we consider 1 over the channel transfer function square multiplied by n0. This gives us this profile. And then we pour water such that the integral of this area is equal to the total power we have. And then we take this picture, we flip it. This will be the power spectral density of the optimal transmit signal. Each one of these little slices is a subchannel in the frequency domain, and we treat these as parallel channels in the frequency domain through the OFDM algorithm. If you take k, so the number of subchannels very large with respect to the length of the impulse response, this is arbitrarily close to optimal capacity achieving for this frequency selective channel. Okay, and this is the information theoretic explanation of OFDM, which I say is widely used. It makes transmission over physical channels formed by a certain impulse response plus Gaussian noise very, very efficient. Okay, so this ends this chapter. A lot of concept to take in. We will go through some details and more on the relation between these information theoretic models and the communication theoretic models that you are probably more used to see in terms of waveforms and modulated waveforms, etc. in the live session. I cannot do a course in communication theory in 20 minutes, so you should be aware of this. If you are not, take it as a hint if you are interested in pursuing more in this direction. And then we will see many other interesting problems related to differential entropies and continuous random variables in the problem sessions. This ends chapter 5, and see you in the live sessions.